exploration is actually analyzing returned samples. And I have been working for, I'm embarrassed to admit, more than 20 years on a problem that is quite vexing to an analytical geochemist, and that is, how do you maximize science and understand valence state in samples that are really tiny? And so this group of people and many more have been working on this problem. So I want to start out by sort of reminding myself and you why we're interested in this problem. Oxygen turns out to be one of the most difficult elements to measure, and yet, of course, it's the most abundant element in the crust of terrestrial bodies. So it's kind of ironic that the element that we have the most of, we know the least about measuring. But of course, it's very important for many, many reasons in geochemistry: phase equilibria, crystallization, metasomatism, et cetera, et cetera. So I won't belabor that, but just say that it's really important that we understand how much oxygen is around. And again, I've known from personal experience that oxygen is very difficult to measure. Now, despite some of the measurements that have been made from spacecraft, in the world of petrology and mineralogy, we don't routinely measure oxygen, and that's because there aren't any standards. There are, you can count them, 10 mineralogical standards for which oxygen has been directly measured, and in particular in this lab. Bill Eman at the University of Kentucky was one of the pioneers of fast neutron activation analysis and supplied oxygen analyses for the few standards that exist. But generally speaking, when you look at geological analyses and mineralogical compositions, we don't have oxygen data, and it's a big problem. In some ways, very surprising given that we're in the new millennium of technology. You'd think we'd have better standards, but we don't. So because oxygen is very difficult to measure directly, we have to use proxies, and of course the proxies we use are to try to understand oxygen fugacity by looking at multivalent cations. And you know, many studies of meteorites have shown, such as the ones here by Barley and Jones, that there's quite a wide variety of oxygen fugacity and represented in our solar system and in various kinds of solar system materials. So again, stressing the importance of being able to make these kinds of measurements. And so, of course, many of you are aware that we put a Mossbauer spectrometer on each of the Mars exploration rovers, and we got some very useful data on ferric-ferrous ratios on Mars, but we'd like to be able to do these measurements routinely on samples on Earth. And surprisingly, again, I've spent my whole career looking at ferric-ferrous ratios and different ways of measuring them in laboratory samples. But boy, doing redox ratios in tiny samples is very, very difficult. The traditional, or not even traditional, the existing conventional techniques for measuring redox ratios all require bulk sample. Wet chemistry, of course, requires grams of sample. Even Mossbauer spectroscopy in the state-of-the-art applications requires about 4 to 10 milligrams. So, of course, for many return samples from missions, we don't have 4 milligrams, or if we do, that's the entire return mass. So there has been a lot of interest, and this is part of our RISE Institute, in looking at methods for microanalyzing redox ratios. And I'm going to speak in this talk about X-ray absorption spectroscopy, which uses a synchrotron. And of course, additional really interesting work is being done by Rhonda Stroud and Brad DiGregorio using TEM, and that's the subject of a poster. So let me talk a little bit about X-ray absorption spectroscopy, since it's probably new to all of you. It's kind of a neat spectroscopy in that because you have a synchrotron, you can knock electrons out of orbitals that are really close to the nucleus. So it involves a very high amount of energy. And different things happen to the electrons as you move them around. They can either stay in the atom or actually get tossed out of the atom. And all kinds of really interesting things happen when you remove a core electron. They trickle down, there's a bunch of different transitions, and you get a typical XAS or X-ray absorption spectrum that looks kind of like this. Let's see, there we go. Most of them, and these I'm going to focus on iron just because that's the one that's been the most studied. They have a sort of a characteristic appearance. There's a pre-edge region, which is the lower probability transitions, a main edge here, and then what we call the XF region for extended X-ray absorption fine edge stuff, and that's the even additional transitions, and most Xene spectra have a profile that looks something like this. Again, I could probably talk for hours on that. So now I want to sort of stress some of the difficulties and interesting things about using X-ray absorption spectroscopy that are kind of the same and different from all the other kinds of spectroscopy we've been talking about at this meeting. So the first one is that although we collect routinely all this data from the pre-edge all the way into the XF region, it's traditionally been thought that all the action was actually in this little teeny blip of a pre-edge. And so for years, and I mean like for 25 years, people have been doing Zane's spectroscopy of iron pre-edges and looking at the pre-edge and trying to deconvolute it. But the pre-edge is very confounding to a spectroscopist like me because the intensity of the peaks are not a function of the abundance of the thing that we're measuring. They are a function of the distortion of the site. So this makes for really interesting spectroscopy. You know, when you look at like minerals with 5-fold coordination sites, you get these whopping big peaks. When you look at even silicate minerals where the iron is in tetrahedral coordination, you get huge peaks, but iron in 6-fold coordination, you get tiny peaks because they're more symmetrical. So it's a very confounding kind of spectroscopy, and you have to sort of change your way of thinking to try to understand how we're going to get quantitative information out of spectra like this. And as a case in point, here is a set of spectra. These are all from garnet. I'm going to use garnet as an example, even though it's not relevant to planetary. It was one of the first materials that we studied in detail because it's isometric. It doesn't have any preferred orientation. So these are a bunch of garnets with varying ferric-ferrous ratios. And you can see that there's a lot of information in an X-ray absorption spectrum, and much of it we don't understand. That's another little confounding problem with XAS. There is no good theoretical understanding of what gives rise to which peaks. So we have to do everything empirically. And it really has felt for 20 years like we're through a glass darkly until about the last couple of years when we start to understand how to deal with these. The good news, though, is that synchrotrons and X-ray absorption spectroscopy have been successful in looking at a whole bunch of different elements that occur in multivalent states, including the ones shown here: iron, manganese, chrome, vanadium, europium, and titanium. So if we could just figure out a numerical model for understanding how to interpret valence state measurements out of these things, we'd be golden. And that's sort of the object of this study. And then one last thing to realize about synchrotron radiation and X-ray absorption studies in particular, and that is that unfortunately for us, synchrotrons are polarized. You don't think about this until you realize that a synchrotron is basically just mirrors controlling photons circulating in a vacuum ring. And by virtue of the fact that they're circulating in a vacuum ring, they are plane polarized. And what that means is that when they interact with the material, it creates what we call X-ray plucarism. So the minerals interact anisotropically with the photons in the reactor. So again, a little problem. We're used to dealing with powders, but when we start looking at tiny returned samples that we maybe only have one crystal, we have to start to think about, shoot, how do we deal with anisotropy in our minerals? Okay, so one of the goals of our RISE Institute then is technique development to try to realize the potential of X-ray absorption spectroscopy and use it to study planetary materials. And so I want to give you a little snapshot of what we're doing. We have selected 20 different geological compositions that are hopefully representative of naturally occurring materials on planetary surfaces. For those of you who aren't familiar with this, this is a total alkalis versus silica diagram, and it shows the different fields for different kinds of igneous rocks. So Molly McCanta at Tufts University has synthesized each of these compositions at 4 different FO2s. Let's see, iron wustite, air, CO2, and QFM. And we are measuring each of those samples with Mossbauer spectroscopy, which is taking a long time. But we are using Mossbauer as our reference, so we know how much ferric and ferrous iron is in each one. We are acquiring the measurements, the X-ray absorption spectra from all 80 of these samples, not only at the National Synchrotron Light Source, which is about to close. We're just going to finish those measurements hopefully next weekend, and also at the APS in Chicago, and then eventually at the new NSLS2 at Brookhaven. Now, so these are some of the results. These are what the data look like. And you know, I've extracted the pre-edges from here so you can kind of get a sense of what we're dealing with. Certainly glasses, this particular composition, samples that have 10% ferric have the same or similar spectra. The one that's very oxidized has a different shape of pre-edge. And so you would think from this that we could probably figure out a way to numerically figure out how much ferric and ferrous were present. However, it's not that simple. And now I go back to some garnet data. This is a suite of garnets, and these numbers here refer to how much ferric iron is in the sample. And you know, if we in planetary think that we have problems interpreting reflectance spectra, imagine these nightmarish spectra. we spent many years trying to figure out from these data some easy way to understand how much ferric iron was present. And one of the first things that was done was based on a paper that was written in 1995. It was decided that, well, maybe if you sort of look at each of these individual spectra and you calculate the average position in energy of the pre-edge, maybe that would give you ferric iron content. And actually, it works sort of remarkably well. These are some data using that model. You know, you get an R squared of 0.92, so you can kind of sort of measure ferric ferrous if you figure out the pre-edge position and you average out all those bumps. But clearly, as a spectroscopist, you look at those bumps and you think, hey, this is telling us something. We need to understand this better. So another worker who's now at ANU, Barry et al. In 2010, tried using data in the XF region. So he observed that in his spectra, there were some little peaks and bumps here. And so he did, I mean, it's amazing what he did. He eventually came up with this algorithm that says, well, hey, what if I ratio the intensity here to the intensity there? Does that let me predict ferric ferrous? And so he got a plot that looked something like this. So, you know, again, not a bad R squared, but completely empirical again. So we came along and looked at this situation, and about 3 years ago a light bulb went off in our head, and we realized that we could use some of the machine learning techniques that we're using for the ChemCam instrument on MSL and apply them to Xray spectroscopy. And so our first attempt was just to use partial least squared, which is exactly what we're using for ChemCam, to the task of interpreting data from XAS, and in fact it worked brilliantly well. You can see the R squared here is almost 0.99. So multivariate models have a tremendous amount of potential. And the thing that I wanted to stress about these models is really shown on this slide. So let me spend a little bit of time going over this. So what this is it's two different garnet spectra. Again, almandine, which is the ferrous end member of garnet, and andradite, which is the ferric end member of garnet. And you can see that the spectra are different. The pre-edges, you can see, are slightly different. The ferrous one has a higher energy peak than ferric. So this is sort of the first area of the spectrum where people looked. And surprisingly, almost all of the literature for iron Xanes uses only the pre-edge region and ignores everything else. Now, plotted on here are not only the XAS spectra in the thick lines, but also this little dotted line stands for the PLS coefficient, which stands for the partial least squared coefficient. And what this is it's telling you, when you do a multivariate analysis of a set of spectra, you are using all the data points in the spectra. You're not particularly biasing it by telling it to look in any particular location. And as a result, the partial least squares algorithm will spit out and tell you the magnitude that each channel has on the results of the regression or on the predicted variable. And so you can see that, yes, in fact, the position of the pre-edge, you can see there's a little blip in the PLS coefficients. It does have a little bit of an effect on predicting ferric, but clearly way better areas for understanding the valence state of iron in this sample are here and here and here. So what's interesting about this is that now I can design, I could if I wanted to, if I were building a spacecraft to do this, I could pick just those 3 channels and use them confidently to predict the variable I'm interested in. So those of you in this audience who are thinking about other kinds of spectroscopy should be catching on to the fact that this kind of machine learning technique, which identifies channels that are useful in predicting variables of interest to geologists, is extremely powerful. The whole field of understanding spectroscopy through machine learning techniques is in its infancy, but it is tremendously powerful. And I'm certain that in 10 years when we attend geological conferences about spectroscopy, we'll all be using machine learning, and we will get away from trying to assign things to individual peaks, and we'll be at more of a broadly based approach like this. So how does this apply back to the goals of our RISE Institute? By 2016, we expect to have a little software package that will be in use at every synchrotron around the world. And when anyone wants to analyze a glass and figure out its redox state, they will simply plug their spectrum into this into our software, and out will come their ferrous ratio, complete with error bars. So tremendously powerful. And then just to sort of show that technique development, although it's not been emphasized much at this conference, it has a very important role to play in enabling and helping with solar system exploration. And of course, as I've shown you, the capability of analyzing redox state is really important for us in terms of understanding the solar system. We're creating this calibration for glasses, and then we'll move on to doing individual minerals. And what's nice about this is not only does this have application, of course, to the very important questions we all want to know as planetary scientists, but this algorithm will also be useful to the broader geological community and to material scientists and anyone who studies glasses. So it's really nice to be doing things that are directly exportable and have broader impacts. So thank you very much.
Yes, please. Can you identify yourself?
Oh, I'm sorry. Hannah Nesbitt from Stony Brook University. Years ago, dare I say, as much perhaps 20 years ago, Steve Sutton and Sasha Bight were initially working on calibration and the ferrospheric ratio in glasses using Xray. At that time, we tried it out.
We tried it out, and one of the problems that we encountered, which they had already pointed out to us, was that in the region of greatest interest to us, which was down at low ferrous ratios, right, or high ferrous ratios, it really was not very usable, and particularly around 10% to 20% of ferric to ferrous ratios. So has that changed now? And
yes.
So with what kind of accuracy now do you think we are able to look in that region?
In a garnet, which is the only thing.
Oh, I'm sorry, glasses as well.
Yeah, right. Yeah. In a garnet, for now, all I can say is our accuracy is better than plus or minus 5%. I can tell you, I can answer that specifically once we finish measuring all our standards.
Right, for the glasses.
You have to realize what a monumental task this is.
Absolutely.
Each of these Moss-Bauer spectra takes a week to acquire, and we've got 80 of them. And I have a few other things going on my Moss-Bauer, so it's taking us a while to get them all through the system. But once we get them all quantified, I'll be able to answer that very quantitatively.
Carly?
This is really fun, Darby. I look forward to seeing your results. I have a question for you of what makes me uneasy, though, and that is the procedure you described, which looks gorgeous, is a couple steps removed from the basic physics of what's happening in the minerals. And of course, we want to know for these features what caused them, why, and the physics is fundamental. So how are you going to, or
Amen, Carly. When I first started doing it, there's a theory here that says that you can relate Zane spectra to something called the Z+1 model. So you can relate Zane spectra of iron to spectra of cobalt, which is the next thing up on the periodic chart, because the theory says that when you take an electron out of the 1s orbital, temporarily the nucleus is fooled into thinking it has an extra neutron. So there were some early attempts to try to interpret mineral spectra of Zanes using the Z+1 model, but they didn't work very well. So essentially, and unfortunately, in this kind of spectroscopy, there is no good theoretical model for it. So yeah, it makes me uneasy too, Carly, to let go of what's causing all those interesting features, but we don't have a model that can explain them.
Okay, fair enough.
Sadly.
Okay, thanks, guys.